Okay, this is part 2 of Unit 3B, and we're looking at numbers and different perspectives of numbers. In this case, we're looking at the perspective through estimation, and we're looking at the problem, could an average person lift $200 in quarters? Interesting question there. Now, it's really hard to envision what $200 in quarters looks like. Is that a big mass that is difficult for a regular person to lift? Is it a little handful? Is it a bucket full? It's hard to imagine. So what we can do is we can try and change our perspective in order to get a better idea. And so the first thing, if you were to look this up, is each quarter is about 0.2 ounces, so 0.2 ounces for each quarter. And then the other thing we've got to remember is that $200 is equivalent to 800 quarters, because there are 4 quarters for every dollar. And so now we've got some information where we can, probably the best idea would be to take the number of quarters, and change it into pounds, because ounces isn't always something that we are referring to unless it's something really small. And 800 quarters, I think pounds would probably be a little bit better idea for us. So what we're going to do is we're going to take our 800 quarters. So we have 800 quarters, and remember it's 0.2 ounces for every 1 quarter. So we're just going to convert our units here, doing unit analysis, and then so that it cancels out the quarters, and then 1 pound is equivalent to 16 ounces, so that's going to cancel out my ounces, and I'm now going to be left with just pounds. So if I take 800 and times it by 0.2, times it by 1, and then divide all that by 1 times 16, you actually get 10 pounds. And now that puts in perspective. Could an average person lift 10 pounds? Yes, I think that's very plausible, that the average person would be able to pick up 10 pounds. So yes, in this case, this does seem plausible. But again, when we change the perspective from number of quarters to pounds, we're able to make a much more knowledgeable conclusion with that statement. Okay, another way that we compare numbers is, or that we look at perspectives of numbers, is through comparisons. So this comparison is just a selection of energy comparisons. Okay, so for example, the amount of energy released by metabolism of 1 average candy bar is 1 times 10 to the 6 joules. Okay, remember joules is a unit of energy. And you can look here, the energy need for 1 hour of running for an adult is 4 times 10 to the 6 joules. So if you're running for an hour, you need approximately, and if you're 10 to the 6th, that's going to take you up into the millions. So you need approximately 4 million joules to run every hour is what your body needs, and so forth. So you could go down and look through all of the rest of those, but these are just some selected comparisons that were put together in the text. And this first question here, number 39, we're looking at how many average candy bars would you have to eat to supply the energy needed for 8 hours of running? So we're looking at candy bars, and so remember that 1 candy bar was 1 times 10 to the 6 joules. Okay, that was from this table up here. That was the first column, or row I should say. And so the next thing we're going to be looking at is, well, we're running for 8 hours, and we want to figure out how many candy bars in the end. So for every 1 hour, it was 4 times 10 to the 6th joules. And that's for 1 hour, but we need 8 hours. So 8 times 4 times 10 to the 6th joules is how many joules of energy we need in order to run for 8 hours. Then we are going to convert from joules to candy bars. So remember that it was 1 times 10 to the 6th joules for every 1 candy bar. Okay, and the joules will cancel, and I can multiply the 8 times 4 there, so that would be 32 times 10 to the 6th over 1 times 10 to the 6th. And the units now are candy bars. Okay, and the nice thing about scientific notation is we have 32 times 10 to the 6th over 1 times 10 to the 6th. So we can kind of just analyze these numbers and then the powers of 10 separately. So 32 divided by 1 is 32. 10 to the 6th divided by 10 to the 6th is actually just 1. So you get 32 times 1, or just 32 candy bars. So you would need 32 candy bars to supply yourself with enough energy to run for 8 hours. Although I wouldn't recommend, throwing down 32 Snickers or something before you go running. Doesn't sound like that would go over too well. But that's the idea. So, again, now we can see, running 8 hours, we get 32 million joules is how much we need. But, what does that mean in terms of something that makes sense to us? Well, 32 candy bars, okay, we can kind of wrap our head around that. So that's making the comparison. So next, how many liters of oil are required to supply the electricity needs of an average home for a year? So if you look up here, so energy released by burning 1 liter of oil, so that's 1.2 times 10 to the 7th joules. The average daily rate or use of energy in a home is 5 times 10 to the 7 joules. Okay, so we get that information, and now we can start to try and make some comparisons. And so again, we had 1 liter of oil was 1.2 times 10 to the 7th joules, so that's how much energy we can get out of 1 liter of oil. Okay, so then when we look at, let's just say, in 1 day in a home, we get, that was 5 times 10 to the 7th joules is how much energy is expended in 1 day. And so now let's go ahead and we're going to change this from 1 day. Well, we got to go from days to years, and then we need to go from joules to how many liters of oil. And so as we start this one off, each house uses 5 times 10 to the 7th joules for every 1 day. And so we're going to change days now into years. So there are 365 days for every 1 year. So that now gets us into years, so that's per year. Now we need to change those joules to liters of oil, and so I'd need my joules to cancel. So I have 1.2 times 10 to the 7th joules for every 1 liter of oil. So now my joules units are going to cancel. So this will become 5 times 10 to the 7th times 365 over 1.2 times 10 to the 7th. And that was all there because we had times 1 times 1. And again, this is in liters per year. So again, the 10 to the 7ths are going to cancel out here. So we do 5 times 365 and divide it by 2. Well, that's liters. That's L per year. Okay, and that's roughly 1,520.8 liters per year. So to power a house, we can look at that and say, well, 5 times 10 to the 7th joules. A lot of people don't talk in terms of joules, and that's for one day, and then you times that by 365, and that's for the entire year. But again, that number is a huge number, and we can't put in perspective. But when we compare it to, well, you would need to burn 1,520.8 liters of oil every year to power that home. That number we can put into much more perspective. So when we compare the two, we again can create a little bit more meaning. So that's a look at comparisons and putting things into perspective.